All right, so when it comes to small AI, the kind that might end up running on your phone, we've pretty much nailed the data recipe. We know what to feed it. But, and this is a big but, that's only half the story. The real mystery, the thing we're going to dig into today is what's the best way to actually build one? Yeah, that exact question is what a huge new study is all about. We're moving past the data discussion. We're talking about the AI's actual blueprint, its architecture, its shape, its core design. What really works when you're trying to build something that's small, but still incredibly smart?
And this really lays it all out, doesn't it? On one side, you've got the data recipe. That's pretty much a solved problem. We've got that down. But on the other side, model design is just a big old question mark. And believe me, that's where things get really, really interesting.
Okay, so let's jump into the first part of this investigation. Before they even started looking at all the fancy brand name architectures, the researchers took a step back. They asked a much simpler, more fundamental question. Does the actual shape of the model even matter?
So here's a good way to think about it. Let's say you have a set number of digital bricks, those are the parameters, to build your AI. Is it better to build a wide, short wall, or should you stack those same bricks up high and build a tall, thin tower? That, right there, is the classic depth versus width debate.
So naturally, they ran an experiment. They built 7 different models, and here's the key. They all had the same number of bricks, around 70 million parameters. The only thing they changed was the shape. They tested everything from a super wide 4-layer model to a crazy deep 64-layer one. Now, you'd think the performance would just change on a nice smooth curve, right? Like as you add more layers, maybe it gets a little better, then maybe a little worse. Well, that is not what happened, not even close. The results were, well, they were a huge surprise. Instead of that smooth line everyone expected, the models just split into 2 completely separate groups. It was wild. They either performed really well, up around 38% accuracy, or they were down in the dumps at 32%. There was almost nothing in between. It's almost like the models either get it or they just don't.
And this quote from the paper just nails it. It wasn't a spectrum of performance at all. It was binary. All or nothing, which of course leads to the big question, why? What's the secret switch that flips a model from that low tier to the high tier?
Well, it turns out there is a magic number. It all comes down to something called the hidden dimension, which is really just a fancy way of saying how wide each layer is. And there's this hard threshold. If the width is 512 or more, boom, the model works well. If it's less than that, it pretty much fails. The only exception is if you use this very specific Goldilocks depth of 32 layers to make up for it. The big lesson here, shape isn't just some minor detail. It's a make or break factor. All right, so we've established that shape is absolutely critical. But what about all those famous AI architectures we always hear about, from the big players like Google and Meta? Do those fancy names actually give you an edge when you're building something small? Let's find out. So the researchers basically threw all the big names into the ring. You've got LLaMA 3, Gemma 3, Qwen 3. And they even tested some more exotic types like mixture of experts and diffusion models. It was a real battle of the brands to see which design would come out on top. And here we go, get ready for surprise number 2. When you look at their average accuracy, they're all pretty much identical. I mean, the difference is so small, it's statistically meaningless. It turns out that all those modern bells and whistles, the fancy math, the brand new techniques, they provide almost zero measurable benefit at this small scale. Wow. So the takeaway here is just totally counterintuitive, right? For these small models, the brand name on the architecture just doesn't matter nearly as much as getting the basic shape right. But that begs the question, if accuracy isn't the thing that separates them, what is?
And this is where the story takes a really interesting turn. We're going to move beyond just raw accuracy and start looking at other super important things, like speed and truthfulness. And this is where an unexpected hero enters the scene.
So check this out, because this shows a really important trade-off. On one hand, you have your standard models like LLaMA 3. They have slightly higher accuracy, sure, but they generate text 1 word at a time. It's slow. But on the other hand, you've got these diffusion models. Their accuracy might be a tiny bit lower, but their speed, oh, it is in a completely different league.
And when I say a different league, I mean it.
How much faster are we talking? 3.8 times faster. That is a massive, massive advantage, especially for anything that needs a real-time response. I mean, think about it. A tiny dip in accuracy for a nearly fourfold increase in speed, that's a trade-off a lot of people would take in a heartbeat. But wait, there's more. Here's another surprise for you. When they tested the models on factuality, which is basically just a measure of how often it tells the truth instead of, making stuff up, the diffusion models won again. They actually scored highest on the truthful QA benchmark. That suggests they're just plain more reliable. Okay, so let's recap where we are. We know shape is king. We know diffusion models are super fast and more factual. So, how do you put those two big lessons together? Well, that's exactly what led to the creation of this new optimized model called DARA 70M. Now, the researchers didn't build this from the ground up. They used a really clever shortcut called WSD conversion. See, instead of training a fast diffusion model from scratch, which takes forever and costs a ton, they start with a standard model that's already trained. Then they just efficiently convert it, basically pouring all of its knowledge into the new super fast architecture. And you want to see just how efficient this is? Look at these numbers. Training a model from scratch takes 1 billion data tokens and 18 hours of GPU time. This WSD conversion method, just 100 million tokens and only 1.8 hours. That is a 10 times improvement in both data and time. It just makes the whole thing way more practical. And this, right here, is the so what of all this research. This is the payoff. The final model, DARA 70M, is literally the best of both worlds. It gets the high accuracy of a standard model, but it also gets that blazing 3.8x speed and the better fact-checking ability of a diffusion model. A total win-win.
So what are the big takeaways from all this? Let's do a quick fire round. 1. For small models, shape is way more important than brand name. 2. Performance isn't a smooth curve. It's a two-tier system. They either work or they don't. 3. 32 layers seems to be that Goldilocks sweet spot for depth. 4. Diffusion models are the champions of speed and truth. And 5. Converting a model is a whopping 10 times more efficient. Got it? Good.
And all of this leaves us with one final big thought to chew on. As we start putting more and more AI onto our actual devices, our phones, our laptops, have we been a little too obsessed with just chasing accuracy? Maybe the new frontier isn't just about being smarter. Maybe it's about being faster. And maybe it's about being more truthful. What do you think?